again, students, we are in Unit 12 over kinetics. Is the speed of a reaction. Our last lesson, factors that affect this reaction. We talked about the temperature, the speed of the reaction, or increase the speed of the reaction because they're moving faster, colliding with each other more with a greater force. Remember, kinetics is all based on collision. Another factor besides temperature, smaller particles contact with each other more often, and the concentration to rate. And increase, if you increase the concentration of one or more of the reactants, that means there are more particles involved in that solution or in that phase of matter, and thus with more particles you're to get greater and thus just react will reduce the activation energy required to occur. What happens then? The energy that is available to reactants then goes faster. So then we talked about reaction rates or rate of reaction, whereby we looked at appearance, how they are related directly via the reaction. Today we're going to focus on rate laws. This big topic with the reactant affects the rate of the reaction because it's not uniformly changed by the same degree. We're talking about that over this lesson. We were in this time. Advised do now /calendar. I believe that this lesson is being presented May 6th, I think. Right. And for those of you, this would be behind that. And as I mentioned in the last lesson, we may not be able to get this lesson. I'm not sure how this the end of the school term is playing out. Honors, I'm looking at that very closely. But regardless of this, and you definitely need to know as you go on in your study chemistry at the next level. And so we made on my Canvas home. And so that we will then move along and get started to talk rate laws. So this up. Okay, so here is where we stopped at the last lesson. Again, we're in Unit 12.1, kinetics. So rate laws. So reaction rates generally increase when reactant concentrations are increased. We just talked about that a minute ago. And decrease with time as the concentrations of reactants are reduced. We looked at a data table yesterday, or last lesson, I should say, that saw that as time passes and the concentration of your reactants decrease, then the rate of the reaction or the speed the reaction occurs is also going to increase because as the reactants are used up and to make products, the number of reactant particles is gone down. And so with fewer particles, you're going to get fewer collisions with a smaller force of those collisions as well. And so the rate is going to decrease over time. One way of studying the effect of concentration on reaction rate is to determine the way in which the rate at the beginning of a reaction depends on the starting concentrations of each reactant. So I have an example reaction here. So following reaction, this is a net ionic equation, by the way. So where the ammonium ion reacts with the nitrite ion to form nitrogen gas and water. So our two reactants are the ammonium ion and the nitrite ion. The rate of this reaction can be studied by measuring the concentration of ammonium or nitrite as a function of time, or by measuring the volume of nitrogen gas collected. We could do any of those three to determine the rate. And all of those rates would be equal as the stoichiometry coefficients, the mole coefficients of all three substances are the same. So this is a 1:1:1 ratio. So the rate of disappearance of our two reactants and the rate of appearance of nitrogen would be numerically equal. Of course, these are negative because concentration is decreasing. This would be positive because it's increasing. But remember, we look at absolute value in terms of rate. So now we're going to study the following data recorded for this reaction. So let's take a look at this data table here. I want you to study it for a minute, and I'm going to ask you this question as you look at it. What's different about experiments 1 through 4 as compared to experiments 5 through 8? So I want you to take a minute, look at experiments 1 through 4. Remember, here are our two reactants, ammonium and nitrite, and here's the observed rate that was, observed in the lab and then measured. We'll be doing this actually in our upcoming lab. And so look at experiments 1 through 4. Look what we've done to the concentrations of our reactants, and then look at the same thing in groups 5 through 8. What did we do to each of these initial concentrations and what happened to the rate? Hopefully by now, while I've been talking, you see a difference between these 4 experiments and these. Did you figure it out? Well, hopefully it's what you came up with. In experiments 1 through 4, we were keeping the concentration of nitrite constant. We were not changing it at all, while we were changing the concentration of the ammonium ion. If you'll notice, the rate of the reaction, the speed the reaction occurred, was changing over the course of those 4 experiments. And as you can see, the rate increased as the concentration of ammonium ion increased as well, which we would expect. But I want you to notice something. With this concentration being constant, all right, then this rate increase was solely occurred because of the change in the concentration of the ammonium ion, all right? We didn't change both of them at the same time. If we did that, it'd be difficult, well, it'd be impossible to tell to what degree each reactant's increase had on the increase in the rate. But by holding one constant and just changing one of them, we can see that the rate change is totally dependent upon the changing of this concentration here. And in experiments 5 through 8, we have just the opposite. Here we kept the ammonium ion concentration the same. We increased actually the concentration of the nitrite ion in each of the experiments 5 through 8. And again, the rate of the reaction increased. Again, we would expect that with an increase in concentration. But here again, this change in the rate was due to the changing of the concentration of the nitrite ion. The ammonium ion was held constant, and so that had nothing to do with the rate change. All right? So, keeping that in mind, let's answer these 2 questions here, which I think we have. So what was being tested in experiments 1 through 4? Well, the effect of the ammonium ion concentration on the rate. Okay. And again, we know that because the nitrite ion concentration was held constant. Okay. On the next page, what was being tested in experiments 5 through 8? Well, we just said just the opposite, right? Just the opposite. In 5 through 8, we were testing the effect of nitrite ion concentration on the rate. Because in those 4 experiments, 5 through 8, the ammonium ion concentration was held constant. Okay? This is just good experimental science procedure. When you're trying to determine how something is affecting the change of something else, and you have a choice of multiple factors, you don't want to change up all the factors at the same time and see what happens then to this other thing you're trying to measure, because then you're not going to be able to tell which one caused what. But if you isolate each of the factors individually and test them like that, then you know with certainty how it affects whatever it is you're trying to determine. It's just good science, all right? Good science procedure. All right, so let me scoot this up. The results indicate that changing either the ammonium concentration or the nitrite concentration will change the reaction rate in the same way. If the ammonium ion concentration is doubled while the nitrite was held constant, then the reaction also doubled. We're going to look at that again in just a second. If it changed by a factor of 4, then the rate also changed by a factor of 4. Well, let's go back and look at that. So let's look between experiments 1 and 2, right? Between experiments 1 and 2, the concentration of ammonium indeed doubled, all right? If you take 0.0200 molar divided by 0.010 molar, you get 2, all right? So the rate increased by a factor of 2. What happened to the rate? Well, 10.8 times 10 to the minus 7 divided by 5.4 times 10 to the minus 7 is also 2. Concentration doubled, rate doubled. We can look at that again between experiments 2 and 3. Again, nitrite's held constant, but between 2 and 3, the concentration of ammonium again doubled. It went from 0.02 to 0.04. 0.04 divided by 0.02 is 2. And if you look at the rate, 10.8 times 10 to the minus 7 to 21.5 times 10 to the minus 7, you divide the second one by the first one, again, you get a number right there very close to 2. So concentration doubled, rate doubled. If it increased by 4, well, if we look at experiments 1 and 3, experiment 1 was 0.01, 0.0100, sorry, to 4 sig figs, or to 3 sig figs, and 0.0400. Well, 0.0400 divided by 0.0100 is 4. So the rate increased by a factor of 4. If you the concentration rather. If you take the concentration 21.5 divided by 10 or times 10 to the minus 7 divided by 5.4 times 10 to the minus 7, again you get a number right at 4. So concentration quadrupled or increased 4, so did the rate. All right. So now so the results indicate that the rate is proportional to the ammonium ion concentration raised to the first power. Raised to the first power, right? Likewise, if nitrite concentration was similarly varied while ammonium was held constant, the rate varies in the same way. Look at that. So an experiment, so these are constant now. Now we're looking at how the nitrite concentration changed. Let's just pick, let's pick 5 and 7. All right. So concentration 7 is 0.0606 divided by the concentration 5, 0.0202. That increased by a factor of 3. All right. 0.0606 divided by 0.02 is equal to 3. And if we check the rates, 32.4 times 10 to the minus 7 divided by 10.8 times 10 to the minus 7. Again, divide those two. That gives you a factor of 3. So concentration increased by a factor of 3, rate increased by a factor of 3. So again, the rates are proportional directly proportional, I should say, to the concentration of nitrite raised to the first power. So the overall concentration dependence can be written like this. We're going to talk about this in much more detail here in just a second. So the rate of the reaction is equal to K. This is some constant, okay? Constant. It's actually called the rate constant. Times the ammonium ion concentration raised to the first power times the nitrite concentration raised to the first power. We have two reactants. So there are two reactants concentrations that affect the rate here. And so they both raised it by a factor to the first power. This type of expression where the rate of the reaction is expressed as a function of the concentrations of the reactants is called a rate law. A rate law. And the constant K is called the rate constant. All right. Each and every chemical reaction has its own unique rate constant, and it can be determined mathematically fairly easily. If we know the rate law for a reaction and rate for a set of reactant concentrations, then we can calculate the value of the rate constant. And I will show you how to do that. These exponents, in this case, they're both 1. These are called reaction orders. What you're going to find very soon here is that the greater the value of that exponent, or the larger the reaction order for a particular reactant, the more changing the concentration of that reactant affects the rate. As you can see, if this was a 2 or a 3, whatever concentration this is would be squared or cubed rather than just to its first power. That's going to increase the rate by a larger factor. So the value of these reaction orders is also very critical in determining the rate of the reaction. So I'm going to show you now how we do all of that. So determining a rate law. The general form for a rate law looks like this. So rate equals K times the concentration of reactant 1 raised to some power times the concentration of reactant 2 raised to some power, etc. If there's only one reactant in the reaction, such as a decomp reaction, then the rate law only has one reactant. It could have 2, it could have more. Just depends on the reaction. The exponents, as I said a minute ago, are called reaction orders, and their sum is called the overall reaction order. So if these were both 1, as they were in the previous example, 1 plus 1 would be equal to 2. That would mean it would be a second order reaction overall. And again, the larger the value of that order, the more changing the concentration of the reactants affects the rate. To find the reaction order for each reactant, you must find a pair of experiments where one reactant's concentration is constant. This is what we were looking at in the data table just a little bit ago. That is the control. That way you can then find the reaction order for the other reactant. Excuse me. So here's a good analogy from biology. I'll bet most of you have done this, if not in middle school, perhaps even you did it in elementary school. When you grow a plant and want to test different variables that influence its growth, water, sunlight, soil type, etc., then you must test one variable at a time, all right, while keeping all the others constant, all right? If you're testing for the amount of water necessary for optimum plant growth, for example, then you keep the sunlight amount and the soil type the same, and you vary the amount of water. That way you know that the change in the growth of the plant is solely a result of changing the water. Keep the sunlight and the soil the same. If you want to test the amount of sunlight on plant growth, then you vary the amount of sunlight that the plant gets over time and leave the watering constant and the soil type constant, etc. Like I said, this is just good experimental science. when you have multiple factors involved that affect another factor, you want to test each of the factors individually, all right, while keeping the others the same. Okay? So, to calculate a reactor for two things. First, by what factor or multiple has the concentration been changed? Okay? Secondly, by what factor or multiple has the rate changed? Right? Just what we were looking at in the data table. How did you change the concentration, and how did the rate change as a result? You plug these two numbers here into this very simple little equation. C to the x power equals r, where C is the number you found right here. By what factor did the concentration change? R is by what factor did the rate change? You plug those two numbers in for C and R. Whatever exponent makes those two equal to each other, that is the reaction order for that reactant. Okay? Let's go to the next page. So X is the exponent that makes C and R equal, and this is called the reaction order for that reactant. And again, let me say again, in order to find the reaction order for a particular reactant, the concentration of the other reactant or other reactants, if there are more than one more, must be constant. Okay? Must be constant. The overall reaction order is simply then the sum of the individual reaction orders. And again, so as stated a little bit ago, the rate law for a reaction is written in general as this. The rate of the reaction equals K, the rate constant, times concentration of reactant 1 raised to some power, times the concentration of reactant 2 raised to some power, where M and N are the reaction orders for each reactant. K is the rate constant. It's a number that can be used to find the reaction rate when the concentrations of any of the reactants are in any way. That's the beauty of the rate constant. Once you know what its value is, you determine and predict the rate of a reaction at any set of concentrations. Okay? All right, so let's run through one. All right. So the following data were collected for the rate of this reaction. Just have a general reaction here, a little combo reaction. A plus B yields C. All right. So our reactants are A and B. And again, in the data table, then we're going to look at the concentrations of our two reactants and see how the rate was depending on what their values were. So it looks like we ran 3 experiments here. For experiment 1, here are our two concentrations. Here's the rate, same for 2 and 3. So the first question is, what experiments would you choose to measure the effect of A on the rate? All right, A. So if you want to measure the effect of A on this rate, you want to leave B constant. Okay, you want to leave B constant. So based on that, we want B concentration constant. And B is constant right here. So we want to use experiments 2 and 3. All right. Remember, B concentration held constant. That is the key in determining how A affects the rate. Okay. So next, let me scoot this up a little bit so we can see these. All right. What is the reaction order with respect to A? All right, so here's where we're going to do the math. Here's our little equation, C to the x power equals R. We are looking at experiments 2 and 3. All right, 2 and 3. So the question is, by what factor did A's concentration change between reactants 2 and 3? Well, in experiment, I should say experiments 2 and 3. Experiment 3, its concentration is 0.45. In experiment 2, it's 0.15. So by what multiple or factor did that change? Well, if you take 0.45 divided by 0.15, you get 3. In other words, the concentration of A was triple between experiments 2 and 3. Since that number is 3, that is our C value, 3 to the X. Next question, how did the rate change? All right, by what factor or multiple did the rate change? Well, 1.80 divided by 0.20 is 9. All right, so the rate changed by a factor of 9. R is 9. So 3 to the X equals 9. What exponent makes these true? Be careful now. This is an exponent. This is not 3x equals 9, because if that was true, x would be equal to 3. This is 3 to the x power equals 9, in which case x equals 2. All right? So this reaction is second order in A. Second order. That exponent is a 2. Makes it second order. Okay, next. C. What experiments would you choose to measure the effect of B on the rate? Well, here again, when you want to measure the effect of B, then reactant A must be held constant. All right? So where is A constant? Right here in experiments 1 and 2. So we want to use experiments 1 and 2. Because the concentration of A is held constant. We determine B's effect on the rate by holding A constant. Okay? Letter D, what is the reaction order with respect to B? I'm going to write it up here so we can keep the data table up here. You may not be able to see that down there. So D. Once again, we're with respect to B. All right, so C to the X equals R. So by what factor did the concentration of B change between experiments 1 and 2? Well, right here they are. All right. So in experiment 2, B's concentration is 0.24. In 1, it's 0.12. 0.2 to 0.24 divided by 0.12 is 2. So the rate changed by a factor or multiple of 2. C is 2. C to the X equals R. C is 2. How'd the rate change? Well, here we go. The rate in experiment 2 is 0.20. In experiment 1, it's 0.10. 0.20 divided by 0.10 is 2. The rate increased by a factor of 2. R is 2. What exponent makes that true? That would be x equal 1. It is first order in B. First order. Before we get too far ahead of the game, I want you to understand the significance of those numbers. The fact that A is second order and B is first order means that changing the concentration of A has a larger effect on the rate than changing the concentration of B. That's what the significance of those reaction order values are. Okay? All right. I think I can scoop this up now. So what is the overall reaction order? This is an easy one. All right? It's simply the sum of your two or however many reaction orders you have. With A, it was second order. And with B, it was first order. So that's it. 3. So this is third order overall. Third order. Write the rate law for the reaction. All right. K equals K. K is the rate constant. Okay, we have reactant A concentration, which is second order. So it'd be concentration of A squared. And concentration of B is first order. That would be a 1. Since that's a 1, we know anything to the first power doesn't change its value. So you can leave one there, or you can take it off. Doesn't matter. So either way, however you want to do it. Okay? This is the rate law for this reaction based on the data that we have analyzed. Okay? Next, using the data in experiment 1, find the value of the rate constant K. All right? We'll talk about that here in just a minute. So I'm going to rewrite our rate law. And now I'm going to go back to experiment 1 and pull the numbers. So let me just flip that back real quick. Okay. So there we are. I think I can erase this now. There we go. So in experiment 1, A's concentration was 0.15, B's concentration was 0.12, and the rate was 0.10. All right? So let's remember those numbers. There we go. There. And we'll plug them in. So the rate in experiment 1 was 0.10. We're looking for K. The concentration of A in experiment 1, we said, was 0.15. That is squared. Here's where you got to pay attention to the reaction orders. And the concentration of B in experiment 1 was 0.12. We have all the numbers we need to solve for K. All right? So we're going to square 0.15, multiply it by 0.12, and divide it out. When you do that, you get 0.0027. Going to divide that out. Divide it out of both sides. And K then, based on the data, these are all 2 sig figs, would be 37. 37. Notice I have left the unit blank for now. We're going to determine what that unit is right now, because it is going to vary according to what overall reaction order it is. And I'm going to show you how we do that. I'm going to show you how you actually determine it, and then I'm going to give you a shortcut. Okay? So, over here, deriving the unit for K. So what we're going to do is rewrite our rate law. So rate equals K times A squared times B. So there was our rate law. All we're going to do now is use units rather than numbers, just units. All right? So remember the rate. Look back at your data table. The rate was in molarity per second. That is the standard unit for a reaction rate. We talked about that the other day, molarity per second. What I want you to understand is that molarity per second, if you remember this from your algebra days, that when you have a unit in the denominator, if you want to bring that unit up top and have it be on the numerator side, that the exponent goes negative. In other words, this is technically molarity to the first over seconds to the first. We don't write the ones, but we understand that they're there. If we want to bring this up here, that is the same as molarity times seconds to the negative first. I hope you've seen that before, because that's going to be important here. All right. So that way we don't have to deal with denominators. All right. So our rate is in molarity per second, or molarity times second to the negative 1. Okay. All our concentrations are in molarity. So this would be molarity squared, and this would be just molarity. All right. And again, based on your work in algebra, I hope you understand that when you take molarity squared times molarity, which remember is also molarity to the first, that the exponents are added, all right? So now we have m times s to the negative 1 equals k times molarity cubed. Okay? We're going to divide both sides by molarity cubed. All right? That cancels. Keeping in mind, this molarity is also molarity to the first. Got to remember that. So when you take molarity to the first, divided by molarity to the third, now when you're dividing exponents, you subtract. So this now becomes m to the minus 2, s to the minus 1. That is the unit for this particular rate constant. Now, let me show you the shortcut. You're going to like this one. All right? The overall reaction order. The overall reaction order is the absolute value, all right? The absolute value of the sum of the unit exponents. All right? In the rate constant. Okay? And remember that s to the minus 1, or per second, is always a part of it. So now let me break that down very simply. All right? So let's take a look. Remember the overall reaction order was third order, right? Third order. What is the absolute value of those two exponents added together? 3. 3. Those add up to 3, absolute value. It's a third order reaction overall. Remembering that s to the minus 1 is always going to be a part of it. All right? Then that means the molarity part has to be negative 2. All right? Has to be. So, a third order reaction, the unit for K is always going to be m to the minus 2, s to the minus 1. A second order, this is overall. This is the unit. Well, they got to add up to 2 now. K would be m to the minus 1, s to the minus 1. The absolute value of negative 1 plus negative 1 is 2. Second order. A first order overall. Now we're just down to s to the negative 1. There is no m in there. All right? We'll talk about zero order here in just a minute. There is such a thing as a zero order reaction. No unit. There isn't one. And if we go the other direction, a fourth order reaction. K's unit would be m to the minus 3, s to the negative 1. Again, the absolute value of adding those two together would be 4. Okay? This is how you actually derive the value for the rate constant, or the unit for the rate constant. This is the shortcut. And you're welcome to use it. Okay? All right, let's go to the next one. Letter H. What is the rate now when concentration is changed to 0.50 and B is changed to 1.0? Okay, this is the beauty of knowing the rate law for a reaction and the value of its rate constant. Because now you can determine what the rate will be under any set of concentrations. All right. So we're looking for the rate now. So here's our rate law again. Rate equals K times A concentration squared times B concentration. Now we're solving for the rate. We know what K is now, 37. We've just determined that, okay? When A is 0.50, that one's squared, and when B is 1.0. And that is just to the first power. Multiply them out. 2 sig figs, 9.3, and the rate here is just like it was before, molarity per second, just like in the day. And that is going to also hold true if we looked at it by units. Remember, K was m to the minus 2, s to the minus 1. Well, the s to the minus 1 is still there. That's the per second part. M to the minus 2 times molarity squared would be m to the 0 times m to the 1 would be m. There it is. Okay? All right? All right, let's go to the next one. Example 4. For the following reaction, A plus B yields C. Here again, we got a combo reaction. The initial rate was measured for several different starting concentrations of A and B, and here are the results below. So again, 3 experiments, did 3 different things here to determine the rate law. All right, so first, reactants. So we need to determine reaction order for A and the reaction order for B. All right, now, if we determine the reaction order for A, remember B concentration has to be constant. Where is B constant? 1 and 3. All right. So C to the X equals R. All right. C to the X equal R. All right. So how did the concentration change of A between 1 and 3? Well, it went from 0.100 to 0.200. 0.200 divided by 0.100 is 2. Factor of 2. So 2 to the X equals. How did the rate change? By what factor between 1 and 3? Well, 16.0 times 10 to the minus 5th divided by 4.0 times 10 to the minus 5th is 4. So R is 4, X equals 2. Second order in A. Now, the reaction order for B. Well, to determine the reaction order for B, that means the A concentration has to be constant. Where is A constant? 1 and 2. So C to the X equals R. So how did the concentration of B change between 1 and 2? Well, in 2 it was 0.200. In 1 it was 0.100. So again, 0.200 divided by 0.100 is 2. So our C number is 2. How did the rate change? All right, between 1 and 2. Well, our rate in 2 is 4.0 times 10 to the minus 5. Our rate in 1 is 4.0 times 10 to the minus 5. So 4.0 times 10 to the minus 5 divided by 4.0 times 10 to the minus 5 is what? Yeah, you're right. 1. Hopefully you remember this now from algebra. What exponent there gives you a 1? Do I hear it? Yeah, I think I did. X equals 0. Remember, anything to the 0 power is equal to 1. So it is 0 order in B. 0 order. Remember that. So our rate law is rate is equal to K times the concentration of A squared times the concentration of B to the 0 power. What did we just say? Anything to the 0 power is equal to what? 1. 1. So rate equals K, concentration of A is squared. So let me ask you this. If a reactant is 0 order, how does changing its concentration affect the rate of the reaction? And the answer is, it doesn't. It doesn't. And that's proven here. We changed the concentration of B. We left A constant. What happened to the rate? Nothing. Nothing. Okay? 0 order. Doesn't mean it's not important, but it means that changing that reactant's concentration does not affect the rate. Okay? All right. Calculate the magnitude of the rate constant. Okay, so let me tell you about the last one. We used the data from experiment 1 to determine the value of K, which was 37, if I remember correctly. What if we had used the data from experiment 2 or the data from experiment 3 and plugged those numbers instead into the rate law? What do you think we'd have got for K? If you said 37, you're right. It is 37. It's the same value. Like I said, all reactions have their own specific rate constant, right? Regardless of the concentrations. That rate constant is exactly what it says it is. Constant, okay? It is a constant. And so here when it says calculate the magnitude of the rate constant, the question is, which experiment's numbers do we use? And the answer is, it don't matter. Doesn't matter a bit, all right? So pick whatever one you want. Won't matter. I'll use experiment 1. Just because it's the first one there, but it certainly doesn't matter. It doesn't matter. Okay. All right. So here's our rate law. Rate equals K times the concentration of A squared. Okay. So our rate experiment 1 is 4.0 times 10 to the minus 5th equals K. A concentration in experiment 1 is 0.100. That is squared. Don't forget that. Now, if we had plug B in here, remember it's B to the 0 power, we'd have plugged 0.100 in there. 0.100 to the 0 power is 1. All right, so here again, 0 order, doesn't affect the rate. So divide both sides by 0.01, which is 0.100 squared. And K then, let's see how many sig figs we got. 2 is our lowest number of sig figs. 1.0 times 10 to the minus 5th. Now, what is the unit for our rate constant? You remember what I just showed you? Well, this is a second order. I guess I could have wrote that up here. 2 plus 0 equals second order. Should have had that written down. My bad. All right. It is a second order overall. All right. Make sure you throw that up there. We need that. All right. So since this is a second order reaction, remember S to the minus 1, as long as it's not a 0 order reaction, is going to be there. And so we only need, with a second order, and the absolute value of these two exponents would have to add up to 2, so that's n minus 1. negative 1, absolute value of those two added up is 2. Okay? So m to the minus 1 is minus 1. Letter C, determine the rate when A is 0.0500 molar and B is 0.10 molar. Ha! Why'd I say ha? I don't care if B is 999 million molar. Not that you can make a solution that concentrated, but it's not going to affect the rate. Right? It's not affecting the rate. Tricky. All right. So, rate equals K times concentration of A squared. So our rate constant is 1.0 times 10 to the minus fifth. A concentration is 0.050 squared. Let's multiply them out. And the rate to 2 sig figs. Oh my goodness. I made a mistake up there. Crap. Oh, my bad. I was looking ahead. Yeah, that certainly is not that. I know a lot of you are out there whispering, he's done it again. Well, you're right. I did. This is actually 4.0 times 10 to the minus third, m to the minus 1, second to the minus 1. So all of you out there that were snickering at me, I deserved it. All right. How many times have I done that this year? Too many to count. All right. So let me fix that. 4.0 times 10 to the minus third. There we go. That's our rate constant. And then 0.05 squared. Now we get 1.0 times 10 to the minus fifth molarity per second. There we go. Sorry about that. Shame on me. All right. Okay, these are rate laws. All right, rate laws. I want to take, based off this lesson, you should be able to do 2 assignments, rate laws, and the one after that, which I believe is entitled Reaction Rates and Rate Laws number 2, which summarizes both of these last 2 lessons over rate expressions and rate laws. So they are related, believe me. So before I finish up today's lesson, I want to actually look at one of your problems on the first assignment that's assigned for today, which is the rate law assignment. Let me pull this, take this down. That'll be our next lesson. Now there it is. So there's our rate laws assignment, the first one. And I want to jump ahead all the way to number 3. Numbers 1 and 2 are laid out pretty much exactly the way we did on the notes in our examples, but I want to jump to number 3 and show you one that's written a little bit differently. Okay. Consider the following general reaction. A plus B plus C yields products. So this has 3 reactants. The following observations were made regarding this reaction. Okay, so the first thing you should notice is that where's the data table? Well, there is a one, all right? But what they've done instead is given you an analysis of the data table in a narrative form. I've seen this many, many times on the AP chemistry exam, also on college exams, whereby you can ask rate law type questions in narrative form, and they're much shorter, all right, as you can see. And you can also transmit this to a multiple choice type answer scenario, which then can be done on a multiple choice type test rather than doing it this way. So I wanted you to see one of these and go through it with you so it wouldn't throw you off. But it's the same exact thing we've done. Instead of a data table, they've given you the information from a data table in narrative form. So The following observations were made regarding this reaction. Doubling the concentration of A doubles the rate. All right? Doubling the concentration of A doubles the rate when holding B and C constant. Tripling the concentration of B has no effect on the rate when holding A and C constant. And tripling the concentration of C increases the rate by a factor of 9 when holding A and B constant. All right? So first, determine the reaction order with respect to A. All right? So we have C to the X equals R. So doubling A, so C is 2, doubles the rate. R is 2 as well. So X equals 1. It's first order in A. Determine the reaction order with respect to B. C to the X equals R. Okay, tripling B has no effect. Tripling B would be 3 to the X. If it has no effect on the rate, then that means the new rate and the old rate are the same. When you divide the two, you get 1. X equals 0. 0 order in B. Determine the reaction order with respect to C. Okay, so C to the X equals R. Tripling the concentration of C, so 3 to the X, increases the rate by a factor of 9. So R equals 9. 3 to the X equals 9, X equals 2. Not 3, 2. It's an exponent, remember? So this is second order in C. Second order in C. Hold that thought 1 second. I'm not leaving you. I'm coming back. Wanted to make sure I don't make any more dumb mistakes today. One's enough. All right. Letter D. What is the overall reaction order? So we have A was first order, B was 0 order, and C was second order. So it's third order. Overall, write the rate law for the reaction. All right. So rate equals K, concentration of A to the first, or just concentration of A. Remember, we don't need the 1. You can put it there if you want. Doesn't matter. I'll put it there for now. B is to the 0, and C is squared. You could leave it like that if you want. There's nothing wrong with it, but you certainly can reduce it. So rate would be K times A concentration. B is out since B to the 0 is 1, and that would be C squared. So, whoops. There we go. So either way is fine. Okay. What is the unit for the rate constant K? What's the unit? Well, it's third order overall, which means the absolute value when you add the exponents has to be 3. So K then would have a value or a unit of, the S minus 1 would be there, and so that would leave minus 2 for M. -2 and -1 adds up to 3 as an absolute value. So how do you know? Exponents, absolute value must add up to 3. Okay? The exponent's absolute value must add up to 3. Letter F. By what factor will the rate change if the functions of A, B, and C are all doubled at the same time? All right. Well, let me scoop this up. We can see a little better. Oh, sorry. Oh, crud. I didn't want to do that. Hey, nabbit. Sorry, leaning over the old desk here. There we go. I'm sure I look very cute now. There we go. Okay. Let me get this out of the way. Okay. By what factor will the rate change if the concentrations of A, B, and C are all doubled at the same time? All right, so here's our rate law. Rate equals K times A times C squared. Remember, B is to the 0 power. We don't need it. All right, so if we double them all, well, doubling B is not doing anything because B is not even in the rate law. So we can ignore that. All right, so let's just look at it this way. So we have K. If we double the concentration of A, whatever it was before, it's twice that. So I'll just put a 2 in there. Again, B doesn't matter because it's not even in the rate law. It was 0 order. And if we double the concentration of C, but that's to it's second order for C, so that'd be 2 squared. All right. Now what do you get? Well, 2 times 2 squared. 2 squared is 4 times 2 is 8. Is K times 8, or 8K. Remember, K is a constant. All right, K is a constant. So it would be 8 times the original rate. 8 times. Okay? 8 times. By what factor will the rate change of A is tripled and C is increased by a factor of 4? Well, at least they wised up on letter G. They didn't ask about B because by now you should know B doesn't matter anyway. All right. So now we got rate equals K. Here's our rate law. Same rate law. A is tripled. So now we've got K times, so A is tripled. Again, that's to the first power. And C is increased by a factor of 4. So now we got 4 squared. All right, 4 squared. So let's see, 4 squared is 16 times 3 is 48. So it'd be K times 48. Again, K is a constant, or 48K. So it would be equal to 48 times the original rate. 48 times. Okay? So I wanted to show you an example of a rate law problem whereby you're not given a data table, but they explain an analysis of the data table in narrative form, and you take it from there. So that completes our lesson on rate laws. Again, after this lesson, you should be able to complete this assignment here, as well as the second one, which is a review of both rate expressions or rates of reaction and rate laws. So be working on those 2 assignments. We're going to have a lab next up, a rate law lab. It's a really good one. And then we're going to go on to activation energy and work our way through to the end of Unit 12.1. So I believe that is all I have for you today. So stay caught up on your work. Again, I encourage you to check your emails daily from me. Make sure that you are checking my Canvas homepage regularly. All right. Remember, there's 4 links on my homepage that take us to all the documents related to e-learning. And so you need to be checking those regularly because they can change, obviously. And I make additions to them and so forth. So, again, that's it for today. This is Mr. Keister signing off. Have a great day, everyone, and see you soon. So long.